I'm going to walk through the 10.4b notes with you. We're going to start going back over some of the polar graphs we ended class talking about yesterday. And we'll get into a little bit of the calculus we'll be doing with polar functions. So, if you recall from yesterday, our functions in polar that are going to give us circles, we have r equals a value c. That's going to give us circles of radius c centered at the origin. And if we have r equals some number times cosine or some number times sine, that is also going to give us some circles, but those ones will not be centered at the origin. So, for instance, if we have r equals 4 cosine theta, if you were to plug in some angles, you would see that we're going to get a circle. If we plug in 0, we're going to be over there at 4, 0. If we plug in pi over 2, we're actually at 0 pi over 2. And if we plug in pi, we actually get negative 4 comma pi, which actually sends us back to where we originally started. Man, I gotta work on drawing circles. That is not the greatest circle in the world. An interesting thing to note for these two circles here at the end, it does not take a full 2 pi angle, I guess, period, to make it around for the full shape. That will come into play when we're talking about integration. Something to note, that we only have to go through the angles 0 to pi to get that full circle. So that is that one right there. If we were to draw r equals negative 4 cosine theta, that is going to be over here on the left-hand side. Again, similarly, if you plug in angles 0 to pi, it'll make that full circle right there. So it's right there. With our sines, as we talked about yesterday, if we have, for instance, negative 5 sine theta, if you were to plug in the angles 0 through pi, you would notice that we are going to get a circle. That is, it's not looking so great. Down here on what we would call the negative y-axis. So that one is that one right there. And if we had r equals 5 sine theta, 2, 3, 4, 5, that is going to be that circle that is up on the positive y-axis. So you'll notice the symmetries that we have, cosines, seeing them, we're normally thinking symmetry along the x-axis somehow. Seeing sines, we're normally thinking symmetry, with the y-axis. Our limasones, we have 3 different cases. They all come from this general format. R equals some value plus or minus some value times cosine, or some value plus or minus some value times sine. And depending on those values, you will get different shapes. So what happens if A and B are the same? So you need to be comfortable coming up with these graphs, not necessarily with a calculator. And how you do that is you plug in some angles. The more angles you plug in, the better picture you will get. As you can see from the tables I've provided in the notes, we're not going to plug in a ton of angles, and they realistically don't give you the best set of points to draw the whole picture, but it kind of gives you an idea. So plugging in these angles 0, pi over 2, pi, 3 pi over 2, and 2 pi, I'm going to give you those values. We're going to get 4, 2, 0, 2, and 4. You should make sure that that makes sense to you, thinking about the unit circle, plugging in those angles into that theta right there for the cosine. Please make sure that that makes sense. But graphing those 5 points, well, I guess 2 of them are essentially in the same spot, so that's not the most helpful when graphing. We are actually going to get a cardioid. So we get cardioids when A and B are equal to each other. And then the plus or minus and then the sine or cosine will give you the orientation of what this cardioid looks like. So these are the points that we're graphing, and that doesn't give you a fantastic picture. But if you remember kind of what a cardioid looks like, or if you want to plug in some more angles to get a better idea, what happens with the cardioid is we will reach back to the pole at some point. So, apologize for me not being the greatest sketcher of these graphs, but there is our cardioid. If you want to look at a better picture, Desmos or your calculator or something will give you something that looks a lot nicer than that, but that's the general shape for our cardioid. What happens if A is less than B? So we're going to graph 2 plus 4 sine theta equals R. Again, I'm going to fill in the table pretty quick here. I would double check, make sure that you understand where these values are coming from. Again, a calculator is not needed for any of those. And if you were thinking to yourself, I think a calculator is required, it is time to spend a little bit more time with your unit circle. So what happens for this one, if I were to plot these 5 points, 2 zeros here, 6 pi over 2 is there, 2 comma pi is there, and then negative 2 comma 3 pi over 2. So in the 3 pi over 2 direction, we're going to go the opposite, a radius of 2. So we're actually going up 2. So what's happening right there, oh boy, I think I drew this a little too tall. We start moving up from 2, 0, up to 6 pi over 2. Then we swing down to the left over on the other side, and we will cross through 2 comma pi. And here is where a few more angles would actually be very helpful. For instance, any angle that you plug in there that makes sine equal to negative 1/2 will give you an idea of where this thing will cross the pole, where it'll be 0. What's going to happen is we're going to have a couple more positive radii plugging in some angles, but eventually we're going to get to a place where we do get that place where we cross the pole, and what happens is we make a loop up through. These are all the radii are negative, where r is negative. And then it actually comes back out positive r's again and completes that loop right there. So if A is less than B, that is going to give us our limacone with a loop. Again, maybe your calculator, if you want to look at a way better picture than what I am drawing. Alright, if we have A is greater than B, like our example, r equals 3 minus 2 cosine theta, again, I'm going to just fill in the table really quick. I think it would be beneficial for you to make sure that those values make sense to you. For this one, you might notice that we don't have any negatives, we don't have any zeros, and in fact, no matter what angles you pick, this is never going to be negative, this is never going to be 0. So if we start at 1, 0, 3 comma pi over 2, 5 comma pi, 3 comma pi over 2, and then back to where we started, that is going to take us right there. We're never going to touch the pole. So what happens here, again, a few more angles would give you a better idea. Our radius actually increases a little bit. I didn't do a very good job of spacing out my points for this one, folks. This is going to look kind of nasty. Yeah, that's not a great picture. Because that thing right there on the top is a little exaggerated. It's more of something like that. This is our limacone, oh, that was ugly, with a dimple. It's kind of little indent that is not going to touch the pole. So again, I might recommend taking a look at a calculator, Desmos maybe, to get some better visuals for these. If you want to get a better drawing yourself, space things out on the axes nicely and plug in more angles. Alright, let's get to the rest of these graphs here. Lemniscates. We're not going to encounter these much, if at all. When you have the one with sine, that is the one that is not on the axes. And I'm just doing my best to sketch this. Something like that. Should be a little bit more symmetric, but whatever. And then the one with cosine. That is the one that is going to be, and I started drawing that the wrong direction, but whatever. That is going to be the one that is on the x-axis. I don't know if we're going to see these a lot, but just in case, there they are. Roses. We're definitely going to be dealing with roses quite a bit. You need to know this for petals. If n, which is on the inside of sine or cosine, is odd, there are going to be n petals. And we are only going to need to traverse the angle 0 to pi to make the full rose. If n is even, there's actually going to be 2n number of petals, and it will take 0 to 2 pi to create the entire graph. The a in this case is going to give you the radius of the petal. So for instance, 5 cosine of 3 theta. This is going to be a rose with 3 petals. The radius of those petals is going to be 5. For the cosine ones, 1, 2, 3, 4, 5, we actually first create this part of the first petal right there. Goes up and around, and then for the 3 petals, goes down here and comes back up and then goes into the second quadrant where it comes back through the pole and finishes making our petal. So what's happening here is if I draw like a axis down the middle of one of our petals, 1, 2, 3, 4, 5. It's got a radius of 5, and if I draw an axis down the middle of the other one, 1, 2, 3, 4, 5. So the petals are all kind of 5 long. Might be easy enough to tell by the picture. That is 0. This is the theta equals 2 pi over 3 line over there, and this is the theta equals 4 pi over 3. That's not necessarily what the angles you're plugging in that make those exact points right there, but you can see how they're spaced on the polar axis. For 5 sine of 3 theta, our first petal, if you start at 0, is going to start at 0. So this one actually starts right at the pole. And if we plug in, say, like pi over 6, for instance, if we plug in pi over 6, what happens? We get 5 sine of 3 times pi over 6, which is 5 sine of pi over 2, which is 5. So plugging in pi over 6, which is something like out there, and that's when we're getting to 5. So for this one, I think we start off going that way, and then I believe we go down, and then I believe we go back up and around. It looks something like that. For this one, those petals lie on the angles pi over 6, 5 pi over 6, and 3 pi over 2. And again, if I were to draw 2, 3, 4, 5, some tick marks to show 1, 2, 3, 4, 5, what the radius value is at the ends of those petals. Because of that 5 right there, they are 5. Okay, video part 2 is where we're going to start talking about slopes and tangent lines. So this was just the graphs. Hopefully this was a decent reminder of some things you learned last year.